Now, binomial theorem is a very powerful result. It gives you a bunch of identities. And those identities, you'll see they are useful later on. Let's try to write some of them ourselves. Okay. So let's go back again and recall what is my binomial theorem. I have x plus y to the power n is n choose 0, x to the power n, y to the power 0, n choose 1, x to the power n minus 1, y to the power 1. You're choosing powers of y here, okay? And then we have n choose n of x to the power 0, y to the power n. Yeah, this is our binomial theorem. Do you agree? Yes. Now, what happens if I take let x equals to y equals to 1? What do we get here? If I put, see, when you have an identity like this in terms of x and y, it means this is true for all x and all y. Whatever value of x you put, whatever value of y you put, this identity is going to be satisfied. Yeah. Whenever you have an identity in terms of variable, that identity is always satisfied, no matter what your x and y are. Yeah, do you understand that, right? What do I mean by that? Say, let's go back to a simpler example. X plus y square equals to x square plus 2xy plus y square, right? What is the meaning of this identity? Well, meaning of this identity is I can take any x and any y. If I substitute that here, and if I substitute that here, these two things will be equal. Yeah. Not only just for variables, they're symbolically equal as well. So if I put x and y equals to 1, what do I get on this side? This side will become what? Plus 1, which is what? 2 to the power n. This will become what? N choose 0. This is 1, this is 1. So 1 to the power n is 1. 1 to the power 0 is also 1. N choose 0. N choose 1. N choose 2. Dot, dot, dot. N choose n. This is one of the very beautiful binomial identity. That if you take n choose 0 plus n choose 1 plus n choose 2, you get 2 to the power n. Okay. And there are many other identities you can get, right? I mean, you can put x equals to 1, y equals to 2. Then you can get different identities from there. Is that making sense to you? Yeah. Okay. What is the usefulness of this identity? We will see that later. For example, I'll just quickly mention to you, we will see this later when you're doing set theory. Suppose you have a set of size 5. How many different subsets are possible? So you can make set of size 0. So pi choose 0. You can make a set of size 1. Pi choose 1. Pi choose 3. And that will be same as 2 to the power 5. So if you take a set of size 5, all the subsets have size 2 to the power 5. If you collect all of them. Okay. But again, I don't want to go there. I just want to very briefly mention to you that this is a very powerful result. Okay. Coming from binomial result. I mean, you just put x and y equals to 1, you get this. So this is what the corollary here is. N choose 0 plus n choose 1 plus n choose 2, blah, 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 until n choose n equals to 2 to the 9. What about here? How do we prove this identity? Anyone from the binomial theorem? Any idea on how to prove this from binomial theorem? Here on one side, you have what? Instead of 2 to the power n, you have what? 0. So what are you doing? You're doing essentially 1 minus 1. Okay. So you get another identity. Let's take same binomial. Put x equals to 1, y equals to minus 1. Then what do you get on this side? LHS is what? 1 plus of minus 1, which is going to be what? 0, which is 0. And that is equal to what? N choose 0, 1 to the power 1, 1 to the power n, minus 1 to the power 0. Minus 1 to the power 0 is what? Is 1, right? Let me just write that down. 1 to the power n minus 1 to the power 0 plus n choose 1, 1 to the power n minus 1 minus 1 to the power 1, so on, adding all of them, dot, 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 n choose n, 1 to the power 0 minus 1 to the power what? N, right? I'm just substituting x equals to 1 and y equals to -1 in the binomial equation here. That's all. Yeah. So this gives me another identity, which is what? 0 equals to n choose 0. 1 to the power n, I can just simply ignore, right? It is a -1, which is something I have to be careful about. Plus, or I can write now. So this is 1. This is going to be what? Minus n choose 1. Then it will alternate. N choose 2, minus n choose 3, all the way till n choose n. We don't know what n is, odd or even. So it's going to be -1 to the power n. Simply leave it there. So this is another binomial identity. Yeah. What is the use of this identity? At this moment, there is no use. Yeah. It's just an identity. We see a nice pattern. That's all. Yeah. The use of this will be later on when you try to apply it in the real life scenario. See, the idea of these results is sometimes they help you to count properly. Yeah, you're counting something and this helps you to count. As I was just saying, giving you indication that if you want to count a subset of size n. Yeah. And not only that, you can apply derivatives here and so on, so forth. It can give a very interesting if you want. But for now, we're just happy with these two results. Okay. Yeah. All right. So far, good. Any questions? Anyone? Yep. There's no need to worry about this. I mean, this is it. There's no application coming for it. Okay. So these are the two binomial results. Now there's a concept of multinomial theorem. So what is a multinomial theorem? Instead of having x, now we can have the same idea here. Instead of having, say, let's expand this, x1 plus x2 plus x3 to the power, say, 2 or power 3, for example. Yeah. If I want to take power 3 of this, by means 2, right? Multi means, well, I mean, multi means anything more than 2. More than equal to 2. Even by is multi as well. So if I have a multinomial theorem, like instead of x1 plus x2 to the power 3, if I have 3 variables, then I want to know the expansion of it. Generally, people are not interested to write the expansion formula like binomial theorem. Here, you just want to say, okay, what is the coefficient of, when you multiply this, what will happen is you will have x1, x2, x3. You'll have a term like that. You will have a term x1 cube, x2, 0, y, x3, what? 0. Yeah. When you take power 3 of this thing, you will have all combinations of x1, x2, x3 multiplying so that the powers add up to what? 3. Exactly like a binomial theorem. Yeah. Does it make sense to you? Yeah. So now the question is, if I take an element like this, say x1 cube, x2 0, x to the power 0. This is one of the elements. Question is, what is the coefficient of this? Yeah. Do you see my question? Yeah. If you expand it, it will have some coefficient, no? Yeah. Let's take an example. It seems like people are. Let's take x1 plus x2 plus x3, the whole cube. No, sorry, whole square. Let's just do square first. It's what? X1 square plus x2 square plus x3 square. See, all the powers are 2. Then we have x1, x2. Power is what? 2. We have what? x2, x3. And then we have what? x3, x1. There'll be some coefficients here. Yeah, we don't know. We'll find that out in a minute. Yeah. This is an example of a multinomial theorem. Yeah. If you square it. Yeah. Similarly, if I cube it, if I have I mean, this is a big list I have to write, but I will just write it down just for the sake of for sake of, if I have x1 plus x2 plus x3 cube, what are all the possible things which can occur? I can have x1 cube, x2, x3. These are power zeros because the power should add up to 3. Then I will have with some coefficient. Okay, we don't know what that coefficient is. We'll find out in a minute using multinomial theorem. Then we have what? If you want to write it in some order, that's fine too. Let's take x2, x3, sorry, x1 squared. Then we can have what? x2, x3 to the power 0, or we can have x1 squared, x2 to the power 0, x3. Then we can have x1, x2, x3 with some coefficient. We don't know what this coefficient or number is. In this case, the number is 1, 1, 1, 2, 2, 2. We will figure that out. But in this case, what is the number here in front? What is the number here? Then we have another expansion. Say, next expansion will be what? Let's take x1 to the power 0. Then we have x2 to the power 2, x3. And then we have plus no, I should have done this because I took linear power. I'm just trying to have some kind of an ordering in my mind. If I take this to be power 2, then okay, this happens or this happens. Now, if I take x1 to the power 1, then I can have either x2 square with x3 to the power 0, or I can have x1 with x2 to the power 0 and x3 to the power 1. Okay. And now I can have x1 to the power 0. I can have either x2 square, x3, or I can have x1 to the power 0, x2, x3 square. Okay. And then there are other terms as well. Okay. So there will be a lot of terms coming here. Do you agree? Yeah. So we don't need to list down all the terms. That's not our goal. Yeah. And at any point, if the mathematics becomes tedious, then that's not how mathematics is supposed to be done. All right. The question is, all these combinations will occur. Okay. Your question is simply, if I take this guy, x1 square, x2, x3. Yeah. My question is, then our question will be, what will be the coefficient in front of this? What is number in front of this? Yeah. Does that make sense to you? This is what your multinomial theorem answers. Multinomial theorem says the following. It will be, what is the power here? 3. So it's going to be 3 factorial divided by, now let's look at individual powers. And here we have what? 1. Multinomial theorem says simply that it's going to be what? 3 factorial divided by 2 factorial, 0 factorial, 1 factorial. That's what multinomial theorem says. Yeah, so in actually, if you do this, you will have coefficient to be 3 for x1 square, x2 to the power 0. Yeah, this is what multinomial theorem is telling you. That's all. Is the idea making sense to you? Yeah. So multinomial theorem gives you the coefficient when you have x1 plus x2 plus x3 plus x4, blah, 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 and you want to raise it to higher power, the coefficient of it. Okay. We are rarely going to use multinomial theorem. Our main goal is binomial theorem. But for future, if you have to use multinomial theorem, now you know how to go about it. All right. So let's look at now a few examples. Okay, so I'm not interested in the first one. You can do that at home. What is the coefficient of x to the power 12, y to the power 13 in expansion, x plus y to the power 25? So how do we go about it? You have how many boxes now? 25 boxes. And out of those 25 boxes, you have to decide whether you want to choose y or x. The answer is going to be exactly the same. Yeah. So out of those 25 boxes, suppose I'm choosing x. So the answer would be what? 25 choose 12. and this is same as what? This is same as 25 choose what? 13. These two numbers are exactly the same, right? Because 12 plus 13 is 25. So either you choose 12 to get, or you get 13 to discard. Okay, so this is the case. Does that make sense? Question here. What is the coefficient in this expansion? What is the coefficient of x squared y to the power 20? If I expand this, what is the coefficient of x squared y to the power 20? Here, in this one. Anyone? That will not happen, boss. You got trapped. You see why it would not happen? Because all the powers which will appear, you add the powers, they should always be 25. If you're raising to power 25, yeah, there's a trick question. I was just trying to see if you can. Yeah, does it make sense to you? Yeah. Because in all the expansion, look at x plus y squared. I mean, just for the sake of it, huh? Let's go back again here. Or let's look at this one here. X plus y to the power 3. What are all the possible combinations? 3 to the power 0. 3 times 3 plus 0 is 3. 2 plus 1, yes, there's 1. 2 plus 1 is 3. Yeah. So only powers can occur when you add the powers, it should give you the n. Okay. Only those are the possibilities in the binomial expansion, or for that matter, multinomial expansion as well. Okay. Make sense? All right. Let's move ahead. So this now, what is the coefficient of x to the power 12, y to the power 13 in 2x minus 3y to the power 25? How do we do this problem? So again, the story is same. The question we should ask ourselves, are we going to choose x or y? Can you make a choice for me? X. Okay. Well, x was loud, so let's choose that. Yeah. So we have what? How many ways can we choose? So we are choosing what? Choosing x, right? So in that case, we have what? We are choosing what x? We are choosing 12 x's, right? So it's going to be 25 to choose 12. We will have, instead of x, we will have 2x to the power what? 12. And then we have minus 3y to the power 13. This is how this element will show up, yeah, in the expansion. And then if you just remove 25, choose 12, 2 to the power 12 minus 3 to the power 13. This is the coefficient of that guy. Of what? Of x to the power 12, y to the power 13. Does it make sense? I took out x out and y out. So that's what, right? Because we are asking for the coefficient of this guy, right? Yeah. In this case, we get powers of 2 and powers of 3 because it is not x minus y or x plus y. It is 2x minus 3y to the power. Is that making sense? Anyone? Questions? Is the pace okay? Now, there is only one recipe to do well in MACM. Either you're a genius, actually there are two. Either you're super smart and everything comes naturally to you. I have only known 10 or 15 people in my whole life who are that smart. I'm not one of them for sure. Other way is you do many problems. Yeah, you do as many problems as possible, then it becomes a second nature to you. Yeah. So I think maybe this second nature is the best way. And even I have seen some super smart people. Oh God, they work so hard for so many years. It's just amazing. Yeah. And of course, I mean, our goal is not to become like, we don't want to become Einstein maybe, but the idea is that we must push to our limits, right? I mean, to see what really is there. Anywho, so this is the idea behind the binomial theorem. Okay. Now, the next topic we want to talk about is about combination with repetition. Okay. So now there are n distinct objects, suppose. Suppose there are and distinct objects. All right. Suppose there are, say, basically 5 different kind of candies. Yeah. Okay. Let's take an example. There are 5 different, and distinct means what? They are distinct objects, right? So there are, say, 5 distinct so there are 5 distinct candies. Okay. Out of that, suppose you want to select 3. You want to select 3 candies. Yeah. And you're allowed to repeat. Does that make sense to you? Suppose, let's say the candies are A, B, C, D. A, B, C, D, E. 5 different kinds of candies. And you want to choose 3 candies out of it. And you can choose all of them to be AA. This is also allowed. Yeah. How many such possible combinations are there? Okay. So you're now doing combination with what? With a repetition. You're choosing basically out of these 5 kind of candies, you are choosing what? You're choosing basically 3 candies, and you allowed that all these 3 candies are actually the same same kind of candies. Okay. Does the problem description make sense to you? Yeah. Or in generality, you have basically n objects and distinct objects. And out of that, you're choosing R objects. How many ways can you do that? And you're allowed repetition. What does it mean? It means that you could take all of them to be the same object. Yeah. How many ways can we do that? Is the statement of problem clear to you? You're allowed combination, but you can repeat as well. How many ways can we do that? Okay. So let's try to come to a formula for this, particularly with this candy example. Okay. Let's see. So here we go. So we have so let's say we can do the following. Let's take the following diagram. Let's make a diagram where we can say star, 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 1, 1, 1. So we have 5 candies. We'll choose 4 lines. Okay. This simply means all the candies chosen are the first kind. Is that okay? Yeah. Or here we can think about this as 1 cross cross 1, 1, 1. This means all the candies chosen are what kind? The second kind. Yeah. If I do this means what? 1 candy is chosen what? The first kind, and 2 candies are chosen what kind? Second kind. Does it make sense to you? Yeah. Let's look at few more combinations. So few more different examples. We have what? X. Let's do 1, 2, 3, 4, and put all of them here. What does this means? This means what? All the candies are chosen from which kind? Fifth kind. Do you see what I mean? Yeah. So you have basically, you'll take 4 lines like that. And then there are these spots: 1 spot, 2 spot, 3 spot, 4 spot, 5th spot. Yeah. And depending on where you're putting your X's, so there are 3 candies being chosen, right? So wherever you put your X, suppose you put your X here and here and here, for example. It means what? It means that so this is for the first one. First kind, you're not choosing any. For second kind, you're choosing how many? 1. For third kind, you're choosing what? 1. For fourth kind, you're choosing 1. For fifth kind, you're not choosing at all. Do you agree with this part? Yeah? Is this making sense? Anyone for which this is not making sense, because this is the very crucial way of solving this problem. Very critical, interesting way of solving this problem. This kind of thing is also called star and bars. They're star. I mean, my crosses are stars and bars. Okay. So what you do is, suppose you have 5 objects to choose from. So you make 4 lines like that. Yeah. And they help you basically partition into 5 spaces. Okay. And then depending on where you put the crosses, you will get basically those many selections. Let's look at another example. Can you give me, can you tell me what combination would you like? Anyone? Like, which of the candies do you want? From which one? First, second, third, fourth, or fifth? And how many of those? Can anyone tell me?
One of them.
So you want what? Fifth one to be 1?
Yeah, and 2 of 4.
2 of 4. First. Okay, so 2 of first means this will be 2 of first. Yeah. Then we have 1, 2, 3, 4, and then we have what? 1 of fifth one. Do you agree with this? This will represent what? This represents how many first candies chosen, how many second candies chosen, how many third, how many fourth, and how many fifth. Does it make sense to you? Yeah. Okay. Now, how many different combinations of these star and bars are there? This is an arrangement, right? You see, this is an arrangement. So how many stars are there? 3 stars. How many bars? 4 bars. So how many arrangements are possible? 7. So we have what? This plus this, which is what? 4 plus 3, right? I'm going to write that as, instead of 7, I'm going to write 4 plus 3. How many stars are repeating? How many bars are repeating? Yeah. All these arrangements correspond to different combination of repetition. Okay. Does that make sense to you? Let's do a little bit of rearrangement. This can be seen as, I just want to make sure that this looks like a formula. This can be seen as 5 plus 3 minus 1, right? 4 can be written as 5 minus 1. Then we have what? 3 factorial. And instead of 4, can I write 5 minus 1 factorial? Yeah. So how many such distributions of candies are possible? If I have n candies and R to choose with repetition, okay? This is a combination with repetition. Then we have n plus R minus 1 factorial divided by, here we have R factorial, n minus 1 factorial. Suppose I want integer solution to the following, okay? So let's see the connection of star and bar with the following. Suppose I have what? x1 plus x2 plus, say, I'm going to do this one. x1 plus x2 plus x3 equals to 9. Okay. So let's see, how am I going to solve this problem? Suppose I want to solve this problem where each of the xi's are greater than or equal to 0 and xi's are integers. Okay. Yeah. Is the idea making sense? Xi's are integer and you have what? You have basically, you want to solve x1 plus x2 plus x3 equals to 9. And you're wondering how many such solutions are possible. How many solutions? You'll say, I'm not getting it. Well, let me give you one solution so that it makes sense to you. One solution is what? Say x1 equals to 0, x2 equals to 1, x3 equals to what? 8. That's one solution, right? Another solution could be, anyone? X1 equals to 3, x2 equals to, x3 equals to 3. This is another solution, right? So the question is, how many such solutions are possible? Yeah. Note, we are only interested in integer solutions. Yeah, 1, 2, 3, 4, 5. In this case, xi is greater than or equal to 0. So it can be 0, it could be 1, 2, 3, 4, 5, all the way till 9. It cannot exceed 9, right? So how can we solve this? So let's think about it as star and bar problem as well. How do we think about it as star and bar problem? So let's see. So 9, right? We have 9 here, right? So let's say basically We have 9 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Yeah. Oh, let's basically, yeah. So we have this thing. Here in this case, suppose, well, I mean, generally bar is used for separating, right? So let's be slightly different and just use cross for this. 1 cross, 2 cross, 3 cross, 4 cross, 5 cross, 6 cross, 7 cross, 8 cross, 9 cross. Okay. So these are, suppose I put 2 partitions now. So I'm going to do what? There are 3, but I'm going to put 2 straight lines. If I put 2 straight lines like that, this means what? X1 is 1. X2 is how much? 1, 2, 3, 4, 5, 6, 7. X2 is 7. X2 is 7. And how much is X3? Do you agree? Yeah. So we have converted our problem now to star and bar problems. Yeah. Why? Because that is the important tool to solve. Otherwise, you will be going crazy trying to see all the solutions, right? Oh, X1 is 1. What about X2 plus X3? What if X2 is 1? X3 is this. X2 is 2. X3 is this. X2, you see what I mean? A lot of possibilities to consider. And particularly, we are not interested in what are the solutions. We are interested in how many solutions. Different story, right? So we just are interested in how many different possible solutions are there, right? So do you agree, if I change these bars around, I will get different solutions, right? Just make an arrangement. Let me just erase this. I just say basically, okay, let me do X, 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 X. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's put 2 bars anywhere. I'll even close my eyes and see if I can do it. Okay, right? Let me just use a different color pen. Yeah, in that case, what do I get? X1 is what? 3, X2 is 3, and X3 is 3. Yeah, this corresponds to the solution you get, right? So how many solutions are possible? They are same as how many ways we can arrange this cross and bars. Oh, bars. Do you agree? So how many ways can we arrange it? There are how many objects here? 9 plus 2. So 11 objects, right? Yeah. So you're doing permutation of 11. So 11 factorial. Out of that, how many stars are repeating? How many stars are repeating? 1, 2, 3, 4, 5, 6, 7, 8, 9. So divide by 9 factorial, right? Because in permutation, if something repeats, you divide by that many. And how many bars are repeating? 2. Does that make sense? Yeah. So these are the number of solutions for x1 plus x2 plus x3 equals to 9. These many different solutions will be there. Okay.